So in this tutorial, I will be talking about thermal noise analysis of switched capacitor amplifier from the high-level motivations of why we want to build amplifiers using switched capacitor circuits, why we want to do thermal noise analysis, all the way to uncover the fundamentals of the elementary building block, the basic, sample, and hold circuits. And eventually, of course, the thermal noise analysis of this switched capacitor amplifier. So, as you are watching the video, feel free to check out the links below for the relevant references on achieving a better understanding of this topic. Also, feel free to leave your questions and comments. I will try to address them at my earliest convenience. So, first of all, why switch the capacitor circuits? I mean, we have the continuous term counterparts already. For instance, the resistive feedback amplifier. Basically, Vout is an amplified version of Vin. Now, similar for the right topology, the switched capacitor amplifier, where Vout equals to CSVin over CF. I will talk about how this really works in a moment. Then I ask myself the question, why even bother to talk about this switched capacitor implementation if we have the resistive feedback amplifier already? So for the left one, something must be wrong. Well, at least not working properly from certain perspectives. For instance, the noise of the input resistors is directly added to the input signal, degraded signal fidelity, signal to noise ratio, or SNR. For this reason, Rin needs to be designed sufficiently small. Nevertheless, a small Rin may create a heavy loading to the stage in front, which could be another amplifier or a signal source with high output impedance. Additionally, for a fixed closed-loop gain, a small Rin leads to a small RF, which degrades the OTA open-loop gain. And as a result, the overall accuracy or accuracy of the closed-loop gain. Then people say if the resistor has impedance and noise issues, why not use capacitance like this? Again, Vout is an amplified version of Vin. Now, this seems very exciting, right? Because capacitor is noiseless and high impedance, at least at low frequencies. But actually, nobody used this. So something must be wrong with this configuration. Well, the major problem is that the OTA input common mode is not well defined. I mean, it's floaty in this case. Now, to address this issue, we can add a feedback resistor RF. And in this case, the input DC bias voltage is determined by the OTA output common mode level. Nevertheless, this RF creates a high-pass filter with a corner frequency of 1 over 2 pi RC. After that, we have the expected flat band amplification. Now, in order to amplify low frequency signals, let's say 1 Hz, the time constant RF/CF has to be designed around 1 second. And if we assume 1 picofarad for CF, which is quite reasonable for on-chip implementation, then 1 teraohm is required for RF. And if we use high resistance poly in our 45 nanometer technology, the minimum area for a 1 kilo ohm square resistor is around 0.06 micrometer square. So in total, we need roughly 10 millimeter by 10 millimeter to implement this 1 teraohm. And let's say if the typical dimension of silicon chips is around 1 millimeter by 1 millimeter, then we need 100 chips to implement this RF, which is absolutely crazy and definitely not the way to go. So instead of using large resistors, we need to find another way around to set the OTA input DC bias voltage. And that's how switched capacitor circuit comes into play. Essentially, it's a two-phase system. While in one phase, we set the OTA input DC bias voltage via unity feedback, while in another phase, we do the actual amplification using capacitive feedback. The detailed operation will be discussed a bit later. Now, I don't want to give you the impression that the left circuit is meaningless or useless. Actually, it's quite powerful in some applications. For instance, neural recording. And there's some very, very clever ways to deal with this huge RF. I mean, a lot of research has been done, and this reference is definitely the most famous one. But it's really outside the scope of this tutorial. So I'm not going to talk about that. Now, I want to look into this from another angle, a historical perspective. You know, in the 1970s, MOS technology became the dominant option for the design of digital logic circuits. At the same time, there's a strong driving force to integrate analog blocks such as active filters into the same digital chip. And this is the time when mixed signal design, I mean a combination of digital and analog, came into the picture. Nevertheless, the integration of active filters using resistors and capacitors to accurately set the time constant R2CF has always been very, very challenging because of the large process variation. I mean, could be as large as 30%. And also the fact that resistors and capacitors do not naturally match each other. For this reason, people started to use capacitors to emulate resistors. And in this case, the time constant is set by the capacitor ratio with a remarkable accuracy of 0.1%. Okay, then why thermal noise analysis? Or maybe first of all, why noise? Well, because the noise of the amplifier may degrade the signal fidelity after amplification. For instance, here we have our input signal, 10 millivolts peak to peak, with a certain SNR. If the amplifier is noiseless, the output SNR remains the same because both input signal and input noise are amplified by the same amount of 10. Now, if the amplifier is noisy, which is always the case, then extra noise is injected into the system, resulting in a lower output SNR. So, ideally, we want to minimize the difference between the input SNR and output SNR. To quantify this, the metric of noise figure has to be introduced. Essentially, it's a measure of how much SNR degradation is introduced by the system. Now, for an ideal noiseless amplifier, noise figure is 0 dB. So, really, to make this amplifier useful in any practical applications, its noise has to be designed sufficiently low. Otherwise, the output signal will be looking like this, kind of junky, or even much worse. Okay, then why thermal noise? I mean, why not flicker noise? Because it's another major noise source in CMOS circuits. Well, flicker noise is actually something quite manageable. I mean, you can use a bunch of tricks to partially mitigate or even completely remove them. For instance, you can increase device area, you can use choppy modulation, you can use correlated double sampling, or auto zeroing, you name it. So ultimately, if you design your amplifier properly, you will be limited by the thermal noise. Okay, so now I hope the high level motivation becomes more or less clear of why we want to do thermal noise analysis of switched capacitor amplifier. Good. So before we move on to the overall amplifier, I want to zoom in a bit to the elementary building block, the basic sample and hold circuits, just to establish some fundamentals. So just a transistor and a capacitor in the simplest form. Well, the transistor is switched on and off periodically. And here we model the transistor as an ideal switch in series with a resistor R, representing the transistor on resistance when working in linear region. Now, ideal switch means zero on resistance and infinite off resistance. So, when SW is high, the switch is turned on, and we say the system is in tracking phase or sampling phase because the output kind of follows the input in this window. And then the switch is off, the output is disconnected from the input, kind of floaty, and we say it's in holding phase because the capacitor holds the sampled value just before. And that's of course how the name sample and hold or track and hold comes from. Now, at the end of each sampling phase, the difference between input and output reaches the minimum as shown in these yellow dots. So instead of looking at the continuous time output waveform, What we really care about are the discrete time samples, these yellow dots. Furthermore, discrete time systems rely on discrete time signal abstractions. So really, there's no reason for you to look at the complete continuous time output waveform. Now, similar for noise, to make life easier, we short the input to ground and then add the noise source for any noisy element. In this simple circuit, the resistor is noisy with a power spectrum density of 4 kTr. And this is a snapshot of a transient simulation. As you can see, we have 0 inputs. So when the switch is off, the output is floating, holding its initial value. Notice that the internal node VR is wiggling around because of the resistor thermal noise. And then the switch is on. The thermal noise gets low-pass filtered, appearing at both VR and Vout. Because of this filtering, you can see that high-frequency noise gets suppressed and amplitude goes down as well. And then the switch is off. The capacitor holds the low-pass filtered version of the noise at the end of the sampling phase. And then this process repeats over and over and over again. So, as mentioned before, instead of looking at the continuous time output V out of t, what we really care about are the discrete time samples, these blue dots. Essentially, they can be obtained by low-pass filtering the resistor thermal noise and then taking one sample every sampling period Ts, as shown in this circuit. So now the question is, what's the total noise power of V out of n? Well, essentially, it's the same as Vc of t, because V out of n is a sampled version of Vc of t. Then the total noise power can be obtained by this integration. We low-pass filter the thermal noise and then integrate all frequencies from 0 to infinity. The final result is this famous kT over C noise. Now, interestingly, this smooth low-pass integration can be represented by a breakwall integration simply by scaling this 3 dB bandwidth by pi over 2, which becomes 1 over 4 RC, the equivalent noise bandwidth. Um, it would be nice to remember this integration because it will be used heavily in our following analysis. Finally, I have to clarify that these calculations are only valid for complete settling, meaning that the spectrum of output samples is white, which is typically true, while for the case of incomplete settling, which is rarely used, you may refer to this reference. Okay, now we zoom out to the big picture, the overall amplifier. As the fully differential system is less intuitive, we will use the single-ended version for our following analysis. So essentially, it's a two-phase system as mentioned before, a sampling phase and a redistribution phase or amplification phase. Now, during the sampling phase, the OTA is a unity feedback, and the node Vx is virtual ground. The input signal is sampled on CS, creating a signal charge of minus CS Vin at Vx. And then the redistribution phase. The input is shorted to ground, and the OTA is in capacity feedback. In this case, the node Vx is again virtual ground, but with a charge of minus CF Vout. Now, the charge in the transition between the two phases must be preserved, meaning that Qx1 equals to Qx2. Just imagine that when we short the input to ground, we discharge the left terminal of capacitor CS from CSV in to 0. And this discharge current cannot go to the OTA gate input, but rather the feedback capacitor CF. So essentially, we transfer the charge CSV in from CS to CF. As a result, V out becomes CSV in over CF, simply a scaled version of the input signal. Now, for noise analysis in the sampling phase, we need to find the noise charge at node Vx, because as mentioned before, this charge will be transferred to the feedback capacitor CF in the following redistribution phase, and then appears as a noise voltage at the output. So for this purpose, we short the input to ground and represent every switch with its on resistance R on and noise PSD 4kT R on. The OTA input referred noise is 4kT gamma over GM. So really the goal is to calculate the total noise charge at node Vx, which is CS Vx minus Vs plus CF Vx minus Vf. Please be very careful that the total noise charge is not CSVX plus CFVX, simply because the capacitor left terminals Vs and Vf are not grounds. Now, this calculation is going to be very tedious and probably pretty messy, because here we have multiple poles and zeros. So, in order to make this world a better place to live in, I'm going to simply ignore all the resistors and their noise contributions. Then you will find life is very beautiful, because now this complex network becomes a single pulse system, like a simple RC low-pass filter. Since gamma is typically around 1, I'm going to approximate the OTA noise as 4kT over GM. So for this simplified circuit, the equivalent resistance is 1 over GM, while the equivalent capacitance is CS plus CF. From the basic sample and hold circuit, we know that the total noise power is this PSD over 4RC, which is again KT over C. As a result, the total noise charge is CV squared, which becomes KT CS plus CF. Now here, I have to clarify that this simplification is only valid when the resistor, on resistance, when this on resistance are on, is much smaller than the OTA output resistance 1 over GM. Because in this case, the resistor noise PSD for KT on is way smaller than the OTA noise for KT over GM. And if we pass them to the similar integration noise bandwidths, the resistor noise contribution becomes pretty much negligible. So intuitively, this really makes sense. Furthermore, this requirement can easily be met simply by sizing the switch large enough, with sufficient W over L. So there might be some kind of area overhead, but typically not a big deal at all compared to the area of the OTA and capacitance. Of course, if you want to consider the resistor noise contribution as well in your calculation, you may refer to the second paper in the reference list. And then for the redistribution phase, the OTA is in capacitive feedback. Once again, we ignore all the resistance and consider only the OTA noise contribution for KT over GN. In this case, REQ is 1 over beta GN, while beta is the feedback factor CF over CF plus CS. Just imagine that if I apply a test voltage VT at the output, beta VT will be appearing at node Vx. As a result, the output current is GM beta VT. Then REQ is VT over GM beta VT, which becomes 1 over beta GM, as shown here, meaning that the output resistance gets amplified by 1 over beta because of feedback. I say amplified because beta is less than 1. Now, what about capacitance? Well, it's simply CS in series with CF and then in parallel with CL. Of course, Miller told us that we can also obtain the result as CL plus 1 minus beta CF, which is exactly the same as below. Then the output noise power is once again this noise PSD over 4RC. Be aware that an amplification factor of 1 plus CS over CF is included, because in this case, the OTA is no longer a unity feedback, but rather in capacitive feedback with an amplification of 1 plus CS over CF or 1 over beta. After some manipulations, we again get this KT over C noise, while C is the equivalent output capacitance. Also, there is a multiplication factor 1 over beta, meaning that this KT over C noise gets amplified by 1 over beta, because again, beta is less than 1. Now, how to understand this intuitively? Well, just imagine that when the OTA is in unity feedback, the sampled noise power is simply KT over C. The multiplication factor is unity. Now, in redistribution phase with a feedback factor of beta, the OTA noise gets amplified by 1 over beta square. Meanwhile, the output resistance REQ gets amplified by 1 over beta. So 1 over beta square over 1 over beta, which leaves only 1 over beta, as shown here in the multiplication factor. Okay, so now we are to combine the two, the noise from the sampling phase and the noise from the redistribution phase. As mentioned before, in the sampling phase, the noise charge at node Vx is kT Cs plus Cf, which is then redistributed to the feedback capacitor Cf in the following amplification phase. The output noise voltage can simply be obtained by dividing this noise charge with Cf, which again becomes kT over C. The multiplication factor is 1 plus Cs over Cf, roughly the closed loop gain. So this is the noise voltage power from the sampling phase. And this is the noise power from the redistribution phase. Basically, the OTA noise gets amplified and then low-pass filtered. Now, the total output noise power is simply the summation of the two. We can do this because the thermal noise for kT over Gn in the sampling phase is not correlated with the thermal noise for kT over Gn in the redistribution phase. Now, if you do similar analysis for OTA offset voltage and flicker noise, you will find that they are cancelled at the outputs because offset and flicker noise are kind of correlated between the two phases. And this probably explains the reasons why we don't care much about OTA offset voltage and flicker noise for this switched capacitor amplifier. Now, typically, people like to do input referred noise analysis. And for that, we simply divide the output noise by the closed loop gain Cs over Cf, and then again sum them together. Okay, finally, I would like to summarize with a few takeaways. So, first of all, for thermal noise analysis, I don't care how complex the system is. I'm always going to do this one pole approximation. I mean, just to find the equivalent R and C. And then the sampled thermal noise power can be calculated as the product of the low frequency power spectral density and 1 over 4 RC, the equivalent noise bandwidth. Typically, the result is in the form of kT over C. We just need to find how many kT over C, the multiplication factor M, which is simply unity for the basic sample and hold circuits. Last but certainly not the least, if you design your amplifier properly, you will be limited by the OTA thermal noise. The contribution from the switch on resistance is pretty much negligible if R on is designed way smaller than 1 over Gm, which is typically the case. And those are some of the references if you want to dive a bit deeper into this topic. So, good luck. I'll see you next time. Simulation in cadence.